Okay, I'm going to get started. Today's class we move on from electrical field, one kind of abstract quantity, and electrical flux, another abstract quantity, to a third abstract quantity, electrical potential. So we're going to talk about electrical potential. Electrical potential is going to be important for the next handful of classes. So this is an important class that will allow us in the next few classes to talk about electrical circuits involving resistors and batteries and capacitors and switches. We'll be talking about man-made electrical circuits with resistors, batteries, capacitors, and switches. We'll also be talking about nature-made circuits with resistors and batteries and capacitors. Neurons are a classic nature-made circuit. In today's class, introducing the electrical potential for the following classes, I want to talk about, firstly, two ways that we describe interactions. They might be gravitational interactions or electrical interactions or other interactions, but one way is with a force perspective, thinking of forces, pushes and pulls. Another one is an energy perspective, thinking of the transfer, the flow of energy. So I'll introduce that. We'll then introduce the concept and define the electrical potential, this new quantity that's going to set up this class and the next few classes. We'll look at the relationship between the electrical potential that we've just introduced and the electrical field from a couple of classes ago. How are those two things connected? They're deeply connected. They're deeply related to one another. And then finally, I'll talk a little bit about electrical potentials in the context of conductors and insulators. Okay. So first topic in today's class. This idea that we can think about interactions, whether it's a gravitational or electrical or other interaction, from two perspectives, energy perspective and force perspective. We've been focusing on the force perspective up to now. We're going to turn to the energy perspective in today's class and later classes. Okay. So you've already met this idea of force perspective and energy perspective in Physics 211 in the context of gravity, the gravitational interaction. In the gravitational interaction, think about an object, an apple, falling under gravity, falling under the Earth's gravitational pull. You can think about that in two different ways. You can think of it from the perspective of the forces that are acting on the apple. You can think of it from the perspective of the change, the transfer of energy to the apple. And that's what this slide is intended to remind you of. It's intended to remind you of your work on gravity and your work on gravitational forces and gravitational energy from 211. Over on the left-hand side is a picture from the force perspective. And over on the right-hand side is a picture from the energy perspective. And downstairs here is really an equation that talks about both the energy and the force perspectives and connects those two perspectives together. So let's just walk through that. From the force perspective, here's the apple. And we've released the apple and it falls under gravity. It falls under gravity because there's a gravitational pull, a gravitational force towards the Earth, towards the ground. And that causes the apple to accelerate, and that causes the apple's speed to increase, to grow as it falls. And so that's what we're seeing here. The energy perspective, that's pictured over here, a bit more abstractly. In the energy perspective, we think about different forms, different types types or brands of energy. In this case, we've been thinking about gravitational potential energy, and we'd be thinking about kinetic, moving energy. And I pictured those as two piggy banks. So here's the gravitational potential energy represented by some cash in the piggy bank. Here's the kinetic energy, moving energy, represented by some cash in its piggy bank. And when the apple falls, gravitational potential energy is released, kinetic moving energy is increased, and that's basically the flow or the transfer of energy or cash, in our analogy, from the gravitational potential energy piggy bank to the kinetic energy piggy bank. So there becomes less, that's the downwards arrow here, gravitational potential energy, it decreased. There becomes more kinetic energy, it increased. And the energy was simply transferred, none lost, none gained, from kinetic energy, from potential energy to kinetic energy. So that's the energy perspective. All these ideas of force perspective, energy perspective of our interactions can be written down as a little summary here, and this long equation of different bits and pieces. This simply says that as the apple falls, there's a change in kinetic energy. Its kinetic energy is growing. As the apple falls, there's a corresponding change in potential energy. Its potential energy is shrinking. That's the reason for the minus sign here, that a loss of gravitational potential energy is a gain of kinetic energy. So these are the changes in energies. That change in energy is accomplished through what we call work done. Work done is a technical word, meaning in physics, meaning energy is transferred through the work done the energy transferred by the gravitational force. So here, this symbol here, W subscript G, is the work done, the energy transferred by the gravitational force, and there's a formula for it, which is simply the product of the force of gravity, times the displacement of the apple. Here's the displacement of the apple. So this equation here, it's really marvelous in that it connects the concepts of energy and the flow of energy from gravitational potential energy to kinetic energy, to the concepts of forces acting as pushes and pulls, and the energy they transfer. Exactly the same ideas, completely the same ideas, apply for electrical forces as they apply for gravitational forces. So what you learn in 211 about gravitational forces, energy force perspectives, applies for electrical forces and the energy force perspectives. And so this is the corresponding slide for the energy force perspective for electrical forces. And I barely had to change the slide for the energy and force perspectives for the gravitational interaction. Over here on the right, now we've got a charge moving in an electrical field rather than a mass moving in a gravitational field. So that's a difference. It's a charge in electric field rather than mass in gravity field. But we still got the idea in the force perspective that there's a force acting on the charge, electrical force, that force causes an acceleration of the charge, causes a growth in the speed of the charge as the charge moves downwards in this picture here. So that's the force perspective. Energy perspective is that there's these two piggy banks. There's electrical potential energy piggy bank. That's a potential energy. There's a kinetic energy piggy bank, again, that's associated with motion. And as the charge falls, the charged apple falls, potential energy, electrical potential energy this time, is turned into kinetic, moving energy. And so energy evolves, is transferred from potential energy to kinetic energy through the action of, this time, the electrical force. Again, no energy is lost, no energy is gained, it's simply transformed from one form to another form. We can summarize all this with an equation. I've written it down here. It's really the same equation. It's just saying that as the apple falls, its kinetic energy grows, right? It's getting faster. As the apple falls, its potential energy is correspondingly shrinking. It's giving up potential energy. The transfer of that electrical potential energy to kinetic energy is accomplished through, technical word, work done, energy transferred by the electric force. So that's the work done by the electrical force, W subscript E, and it's equal to, just like for gravity, the force times the displacement, the force times the distance. And so this summarizes the energy perspective and force perspective, how they're connected for electricity. Okay. Let's just look at an example problem involving this. Just for a little practice. This is a busy slide, but basically in this slide I'm going to imagine a charge moving in an electric field, and we're going to figure out the energy, the change in energy, kinetic energy, moving energy of that charge. Now I'm going to do it. That calculation of the change in energy of the moving charge, the displaced charge, I'm going to do it just for 4 different cases, just to explore the situation a little bit. I'm going to do it for an electron and a proton. So remember, in physics we think of those as the most basic packets of electrical charge. They're sort of units of negative and positive charge. So we'll think of both of those, and then we'll also think about displacements in the direction of the electrical field that's conveying the electrical force, and displacements opposite to the direction of the electrical field that's conveying the electrical force. So we're going to, in total, take 4 cases, positive and negative charge moving in the direction opposite the direction of the electrical field. Okay, so let's get going with this. I think I'll do it on the document camera. But it's in the, obviously it's in the slides. You can look it up in the slides. And I've got to remember how to do this. Here we are. So what we're going to do is calculate the change in kinetic energy. Calculate the change in kinetic energy due to the work that's done by the electrical force as the charge moves in the electrical field. I've made a picture over here. Here's the electrical field. I pictured the field lines. In the question it says it was 20,000 newtons per coulomb in strength. Here's the charge. This is the proton. It has a charge of 1 unit, one basic packet of electric charge. I call that 1e. It's actually 1.6 times 10 to the minus 19 coulombs, that charge. I put it down here. It's positive. And we're going to imagine it being displaced from left to right in the positive x direction. So here's the displacement. And with all these ingredients that I've listed here, I can figure out then the change in kinetic energy of the proton as work is done on it by a force that's created by the charge sitting in the field. So that's the understanding. The change in kinetic energy is going to be equal to the work done by the electrical force. The work done by the electrical force is the force itself times the displacement. The displacement, the force itself is just the charge of the proton multiplied by the electrical field that it's immersed in. That's just the field equation. And so we end up with an equation that looks like this. Q E delta x is going to be the changing kinetic energy of a proton. And Q we know for the proton, 1.6 times 10 to the minus 19 coulombs. E we know, we were told the electrical field was 20,000 newtons per coulomb. And delta x we know is 1 centimeter, or 0.01 meters in SI units. So I just got to plug, now I just got to plug all these things in. I won't write them all down, it'll take me forever. But the answer to it was, I'll call it part 1 of the problem. This part 1 of the problem is when we got a proton and when we're moving towards the right. So part 1 of the problem, if you plug in all the numbers, the change in kinetic energy comes out to be plus 3.2 times 10 to the minus 17 joules. So, few remarks. It's joules because it's an energy. And energy is measured in joules, and a change in energy is measured in joules. It's a tiny, tiny number, right? It's a tiny, tiny number because the amount of charge owned by a single proton is so tiny in coulombs. It's 1.6 times 10 to the minus 19. So it's a tiny number. And then the third point is it has a positive sign. That means that the kinetic energy is increased, has grown. And it got a positive sign, if you think about it, because all the numbers we plugged in were positive. The electric charge, that's positive for the proton. The electrical field was to the right, that's positive. The displacement was to the right, that's positive. So every number we plugged in was positive, so we got a positive change in kinetic energy. In part two of the question, why don't I put the slide on one of them, one of the projectors over here, so we can remind ourselves of that. Brilliant idea, just thought of that. You didn't have to have the same thing on every projector. Not a brilliant idea, because everybody else does that, and I just saw somebody else doing it the other day. Okay. Second part, we've got a proton again in the same electrical field, same distance moved, but it's the opposite direction. So in the second question here, the only difference is I'm moving right to left with the proton rather than left to right. So now I'm moving opposite the direction of the force rather than the same direction as the force. I'm moving opposite the direction of the field lines as I go towards the left rather than in the direction of the field lines when I went towards the right. The only difference when you do this calculation, charge is the same, right? Still a proton. The electrical field is the same. Still the same electrical field. It's the same electrical field in all the examples here. The only difference is that we changed positive 1 centimeter displacement towards the right to a negative 1 centimeter a displacement towards the left. So what's the change? What's the only change that's going to happen in the answer to this problem? Because I'm not going to write all of the numbers in because I just can't. The only thing I'm changing is plus 1 centimeter into minus 1 centimeter, or plus 0.01 meters into minus 0.01 meters. The only thing I'm going to change is a plus sign in the answer to a minus sign. And so we don't need to plug in all the numbers. The answer is minus 3.2 times 10 to the minus 17 joules. Again, joules because it's a change in energy. It's a tiny number again because we've got a tiny charge in this electrical field. But now it's a decrease. The proton's energy has gone down. In the first case, the proton's energy went up as it moved in the direction of the force that was being exerted on it. In the second case, the proton's energy has gone down as it moves opposite to the direction of the force that's acting on it. In the first case, the force was kind of accelerating it, and now the force is decelerating it. Okay. The third example, so this one here, replaces the proton with an electron. So instead of a positive charge, we've got a negative charge. In this third example, the displacement is towards the right, just like the first case. What's the change in kinetic energy there? Well, let's again just compare it to the first example. What's different between this third example and the first example? The field is still the same. The field is always the same in all of these problems. The displacement is 1 centimeter towards the right. That's exactly the same displacement as the first example with the proton moving towards the right. The only difference in this example, the third case, compared to the first case, is that now we got an electron which is minus 1.6 times 10 to the minus 19 coulombs, whereas before we had a, what was it, a proton, which is plus 1.6 times 10 to the minus 19 coulombs. So the only difference here is we're going to have a minus sign rather than a plus sign compared to that very first answer. So this is minus 3.2 times 10 to the minus 17 joules. Joules because it's an energy, minus 10 to the minus 17 because tiny amount of charge, and now a minus sign. We're moving in the same direction as the field, but actually the force, we're moving in the opposite direction to the force. Because it's negative charge, the force is opposite the field. So although the field was towards the right, the force is towards the left. And we're moving opposite the direction of the force, and that force is decelerating us, it's lowering our kinetic energy, it's lowering the electron speed. The final example, well, we've got our electron again. The only difference between the final example and the third example is we've still got the electron, we've still got the same electrical field. It's just that now we're moving towards the left in the fourth example. The displacement is minus 1 centimeters rather than towards the right in the third example where the displacement was plus 1 centimeters. So we've got another minus sign. We've got two minus signs in our equation now. We've got negative charge and we got a negative displacement. And so what's minus times a minus? Minus times a minus is a plus. And so this is going to be plus 3.2 times 10 to the minus 17 joules. And so that's the change in kinetic energy for the final case. In this case, right, the electron is moving towards the left. The force, remember, was also towards the left, unlike the field being towards the right. So the force is in the same direction as the displacement, so that force is speeding up, is accelerating the electron, and so its kinetic energy is growing. Okay, everybody okay with that? I see a lot of smiling faces, some glum ones, but I'll assume everything's okay. Let's see. I was going to demonstrate that there is energy in electrical fields. So the whole implication is here that those electrical fields of the force perspective carry an energy, are energy fields in the energy perspective. So let me see if I can demonstrate that. What I'm going to try and do, this is a lamp. This is a certain type of lamp, and I'm going to put it in the region of an electrical field created by our friend the Van de Graaff generator. So this generator, if I switch it on, this sphere will charge up. This sphere will create an electrical field surrounding the sphere. That electrical field will envelop the entire room. We'll all be bathed in that electrical field. So will this lamp. And I'm going to, without any electrical connections whatsoever, I'm going to light this lamp. That will take energy for this lamp to glow. And so let's see if we can do that. I'm going to set the mood by turning the lights off. And so there's no connections to this lamp. It's just like an old-fashioned fluorescent lamp. And here you see it glowing this beautiful red color just because there's an electrical field surrounding the generator, and that electrical field is a store of energy. It's a reservoir of energy, and we're tapping into that energy here. Hope everybody can see that. Ow. Every time you turn that off, you get an electrical shock. What am I doing? Okay, so that was fun. Let's move on with, we've introduced energy perspective, force perspective. Now let's introduce the electrical potential rather than the electrical potential energy. And we're going to connect it to the electrical field that was related to the electrical force. So that's the plan here. This is my sort of introduction slide for the concept of the electrical potential, the idea of the electrical potential, the definition of the electrical potential. Like we had a similar slide for the concept and the definition of the electrical field. So let me just walk through this a little bit. I guess I haven't put it on both screens. Gosh. Let me set the mood. Oh, no, not turn the lights off, just lower them. For me, there's just some level of light that gives the right ambience for the class. Okay. Remember this slide? No. Here's a charge, and here's a nearby charge. And we're thinking about the interaction of the two charges, Q1 and Q2. And the previous time we met this slide, we said that the charge number 1 is interacting by charge number 2 with charge number 2, because charge number 1 creates around it this sort of shroud or cloud, this electrical field. And charge number 2 is superimposed in that electrical field, and therefore experiences an electrical force. Well, the truth is, the reality is that charge number 1 is surrounded by this shroud or cloud, which we can think of in terms of the electrical field or what we call the electrical potential. So there's two ways of visualizing this shroud or this cloud around the charge that conveys the interaction. One way is through thinking of it as an electrical field. One way is thinking of it as having an electrical potential surrounding it. In either way, charge number 2 then sits in that electrical field and experiences electrical force, or sits in that electrical potential and has an associated electrical energy. So electrical field, electrical potential are partners in sort of understanding, explaining the mechanism of the electrical interaction. They're joined together. There's not one without the other. They're deeply related to one another, and they just do two different perspectives, ways of explaining how the electrical interaction works in terms of forces or terms of energy. Okay. So that's the way I pictured this. Look, this charge Q1 created an electrical field, this cloud, or an electrical potential, which we can also think of as part of this cloud. Because charge number 2 is sitting in that field and potential, it experiences a force, if we're thinking about the force perspective, or it experiences a associated potential energy if we're thinking about the energy perspective. Now, let's talk about these two equations down here, because they define exactly what we mean by the electrical field and the electrical potential. And there's although there's similarities between field and potential definitions, there's an important difference that I want to bring up between the two. So here's this was the field equation. It said that the field at the location of this charge is equal to the force it's experiencing, something we could measure, how much it's being pushed or pulled, divided by the charge that it's owned, also something that we could measure. So with those two measurable things, the force it's feeling and the charge it owns, we can divide one by the other to figure out the field at this location. That's how we define the field. The potential. So V is our symbol for the potential. Delta V is the symbol for a potential difference. The big distinction here is that the potential, what we define is the potential difference between 2 points rather than the field at a single point. So in the picture here, delta PE is the change in potential energy, the difference in potential energy of charge Q when it's located at these two different points. So it's how much the potential energy of that charge changes from those 2 points. Like in the last examples, we were talking about moving a charge from one place to another place, displacing a charge. This is the associated change in potential energy when we displace that charge from between these 2 points here. The potential difference between these 2 points, which is just the delta V, is that change in potential energy divided by the charge. So it's the same sort of idea here, that we can measure the energy change when the charge moves between 2 points. We know the charge of the charge, we can measure its charge, and if we divide one by the other, then we can define or introduce this new quantity, the potential, or the potential difference. So it's rather analogous to the electrical field, but not exactly analogous to the electrical field, because here we just needed, in the electrical case, just 1 point. Here we need the difference between 2 points. The electrical potential has units of, so it's defined as the energy divided by the charge, so it's joules per coulomb. We call those units volts. Kind of like the electrical field had units of, it was the force divided by the charge, so it's newtons per coulomb. Electrical potential is joules per coulomb, but we give it a special name because it's so important. We don't want to keep saying joules per coulomb, we say volts. Okay, so just a few comments on that. I've sort of alluded to some of these comments, but I really want to stress them. The field, the field has a physical significance at every point in space. So you can define the field at every point in space. And if you were to change the field at a point in space, then you would change forces. You would change the consequences. On the other hand, the electrical potential, its physical significance, the only physical significance is the difference in the potential between 2 points in space. So only the difference in potentials between one location and another location is physically significant. So that's an important point. That's these 2 bullets here. A consequence of that is that's quite different from fields, that applies to potentials but not to fields, is you can choose the location of 0 volts wherever you like. You can choose it wherever you like. You can't choose the location of 0 field wherever you like, because that would determine the force. But you can choose the location of 0 volts wherever you like, because only the difference from that location is physically significant. For example, when we talk about, we'll talk about point charges and their electrical potentials, it's convenient and conventional to describe the potential of a point charge where 0 volts is very far away, infinitely far away from the point charge. If you've got 2 plates, 2 charged plates, a positive plate and a negative plate, it's convenient to choose one or the other plates as 0 volts. And then we just describe the other plate as a potential with respect to the 0 volt potential. So we're using this flexibility to pick where we want 0 volts to be for convenience, for handiness in different situations. And we use it differently for point charges, collections of point charges, to how we would use it for plates, say positive and negatively charged plates. So this is a warning about that, because it's a bit of, I think it's a little bit of abstraction. It's a little bit of, well, uncertainty, right? Because you can pick where you want 0 volts. And whenever there's uncertainty in a physics class, that's often not a good thing. But here you literally do have that freedom to pick where 0 volts is. Okay. I want to talk about the connection, the relationship between E and V. Now we've introduced the 2 quantities, electrical field and electrical potential, because they're very closely related to one another. Here's a picture. It shows the force, and it shows the most importantly, the force on a charge, but it shows most importantly a picture of electrical interactions either through an electrical field or or electrical potential. So these are the 2 perspectives that correspond to the force and the energy perspectives. The change in electrical potential in this picture is actually equal to minus the electrical field times the change in position. So that's what I'm trying to picture here. So 2 points, one on the left, one on the right. They're separated by some displacement. I called it delta x. They're in some region of uniform electrical field. I called it E. The potential between these two locations on the left and on the right is just minus E delta x. Now, this equation might seem like that popped out of nowhere. Where did he get that? I just got that, actually. If you think back to the two definitions of the electrical field, one was the field equation, F equals QE. The other was the corresponding sort of potential equation. It was a delta PE, the change in potential energy, equals Q times delta V, the change in potential. If you divide those two equations by the charge, you get this relationship here. So this comes out of dividing this equation here by the electrical charge. If you rearrange it, you get kind of a physical idea of how these two things are connected. If I rearrange it for E, so E equals minus delta V divided by delta x, just rearranging the equation. If you read this, this really says that, so delta V over delta x, the change in potential divided by the change in position, that's kind of the slope of the potential. If it changes a lot, it's a steep slope. If it's changing a little bit, it's a shallow slope. If it's not changing at all, delta V, then it's zero slope. So delta V over delta x is the slope. Electrical field is the negative slope of the electrical potential. So that's the way I think of the connection. The connection between this electrical field, this electrical potential that convey the electrical interactions between electrical charges is that the electrical field is simply the negative slope of the electrical potential. That's how they're connected. So this kind of, when we were visualizing this cloud or this shroud surrounding a charge, it's built out of a electrical field and electrical potential, but they're just two ways of thinking about something that's deeply connected, because one is the negative slope of the other. The field's the negative slope of the potential. Okay. A few examples. Yes?
Is it possible to have a slope of zero? Because doesn't the field inherently get weaker as it goes out?
Is it possible for the potential to have a slope of zero? I think so. This is a good question. Is that your question?
I think so.
Yeah. We'll make it that question. So yes, it's possible. Supposing this is a really good question actually. So let's think of a real concrete example. Suppose everywhere in this room, the potential was 1 volt. So it's 1 volt here, it's 1 volt here, it's 1 volt here. Everywhere throughout the room the potentials are 1 volt. So the potential has zero slope, right? I don't walk uphill in potential or downhill in potential as I move around in this uniform 1 volt potential. Has zero slope, which means that the electrical field is the negative slope of the potential. There's no electrical field in the room. So if you've got zero electrical field, it means that you've got a constant electrical potential. So if that answers your question. Yeah. So it's actually, it's a very important case, right? Electrical field, zero electrical field literally corresponds to a constant potential. Okay. This is and we'll even see it on this picture. There's a case of it. This is a picture, this is a graph, that is about the relationship between the electrical field and the electrical potential, the connection between these two things. So the graph is literally a graph of the potential V, so that's the vertical axis measured in volts, versus the position X measured in centimeters. So it's a map. It's a map of potential V versus position, like we were mapping out the potential in the room. what we see is that if we start from over here at the origin and walk to this distance 5 centimeters from the origin, firstly the electrical potential grows. And it grows steadily from 0 to 30 volts. Then it falls. Over the next centimeter, it falls from 30 volts to 0. Over the next centimeter, it's constant at 0. It's not changing. Then over the next centimeter, from 3 centimeters, 4 centimeters, that electrical potential is decreasing. It decreases steadily from 0 to minus 30 volts, and then it grows back up from minus 30 volts to 0 volts. So we've been given the map of the electrical potential in some region of space. We've been told exactly what the potential looks like in some region of space. If you're told the potential in some region of space, you can then figure out what the field is, because the field is connected to the potential. They're tied together. The field is the negative slope of the potential. So let's start walking through this figure. We're not told it in the figure what the potential is, what the field is, but we can figure it out from what the potential looks like. And that's what I've done in red. So let's think about this first centimeter. What's the field here? Well, the field's the negative slope of the potential. What's the slope of the potential? It changes by 30 volts, goes up by 30 volts, over a distance of 1 centimeter. So the slope is 30 volts per centimeter. That's the slope. But the field is the negative slope. So the field is going to be minus 30 volts per centimeter. And that's what I've written down here. The electrical field is minus 30 volts per centimeter. 30 is the size of the electrical field, so it's a non-zero electrical field. The minus sign is telling us about the direction. The slope was uphill, but the minus slope will be in the negative direction. The negative slope will be in the negative direction. So if we were to picture field lines here, maybe I could have drawn one. It would have been pointing towards the left. That's the meaning of the minus sign here. What about the next centimeter? From 1 centimeter to 2 centimeters, now the potential is decreasing. It's decreasing from 30 centimeters down to, 30 volts down to 0 volts over 1 centimeter. What's the slope of the potential there? Slope is the change in potential, minus 30 volts, divided by the displacement, the change in position, that's 1 centimeter. So the slope is minus 30 volts per centimeter. But remember, the field is the negative slope, so the field is minus 30 volts per centimeter, which is positive 30 volts per centimeter. And so that's what I wrote down here. The electrical field is plus 30 volts per centimeter, the size is 30 volts per centimeter, but the plus sign is meaning now the field has swapped directions. Now it's pointing towards the right rather than towards the left. Okay, what about this region here? The electrical field, what's the electrical field in this region here? We're told the potential. The potential does not change from 2 to 3 centimeters. It's actually, in this case, 0 volts at 2 centimeters. It's 0 volts as you walk to 3 centimeters. So the field is not changing. So what's the slope of the potential is not changing. What's the slope of the potential? Slope of the potential is delta V over delta X. Delta V is 0 from 2 to 3 centimeters. Delta X is 1 centimeter. 0 over 1 centimeter is 0. The slope of the potential from 2 to 3 centimeters is 0. And so the field in this region is 0. This is a region of a field-free region, no electrical field. It would actually be 0, the field would be 0 whether the potential was 0 volts, which is this case, but even if it was constant at 1 volt, or constant at 10 volts, constant at minus 10 volts, the field would be 0 because the potential is constant. Okay, and so on and so forth, right? That's how you can, if you got a graph of potential versus position, you can read off this graph now what the field looks like, because it's simply the negative slope of the electrical potential. Going the wrong way. Okay, I wanted to make one other point on this slide. This has to do with positive and negative charges. They experience, in the same electrical field, they experience forces in opposite directions, for example. And they would, in the same electrical field, they would tend to move in opposite directions. This is the peak of the electrical potential in this landscape. So this, you can think of this as like a landscape on Earth, maybe a gravitational landscape, but it's an electrical landscape. In an electrical world, there's peaks. This is, Mount 30 volts, and there's valleys. This is valley minus 30 volts, and then there's a plateau here. So it's a elevation map of the electrical potential. If you're a positive charge, and you're located at 1 centimeters, then that's the highest amount of electrical energy that you're like at the top of the mountain. Because the electrical energy of a positive charge at this point would be the 30 volts times the positive charge. It would be a positive amount of energy. If you're a positive charge and you're at the bottom of this valley, that would be the lowest amount of electrical energy you can have, because it would be your positive charge, Q, times the minus 30 volts here. And a positive charge, if you're at the top of the hill here, you would tend to fall or roll down to the valley, right? For a negative charge, everything's reversed. Absolutely everything is reversed. So a negative charge, this is the high. If you're a negative charge, like an electron, if you're located here at 4 centimeters, that's your greatest amount of energy, electrical energy. Because your negative charge times this negative voltage, minus 30 volts, becomes a positive number. And so this is a large positive energy, electrical energy, for a negative charge. So this is for a negative charge, this would be like the top of the mountain, whereas it's the bottom of the valley for the positive charge. Likewise, upstairs here, if you're a negative charge, this is your lowest, your most negative potential energy. Because remember, you're a negative charge, you're multiplying that by your positive potential of 30 volts to get your electrical energy. That's going to be a negative number. And so this is the smallest, the lowest electrical energy you can have. So if you're a negative charge, here you're really, if you're located here, you're really standing on the top of a mountain, and you would fall downwards to your valley, which is here. And so positive and negative charges move in opposite directions. We know that in the same electrical field, because the forces are in the directions or opposite the directions of the electrical field. They roll up and down electrical potentials in the opposite directions because of their negative charge too. Does that all make sense? Okay. I just want to make one quick, I threw it in here, just one quick remark on conductors, because we talked about the properties of conductors in terms of charges and fields in the neighborhood of conductors. I just want to supplement that, add to that. Well, what about charges, fields, and potentials in the regions of conductors? And actually, this comes to your question again about zero fields and constant potentials. So here's a conductor, this light blue oval, and we said this conductors have certain characteristics with respect to electrical fields, electrical potentials, and electrical charges when they're in equilibrium, when they're kind of stable, when they're in equilibrium. There's zero electrical field inside the conductor. The electrical field at the surface of the conductor is always perpendicular to the surface of the conductor. And the charge, if there are regions of positive or negative charge in the conductor, they're always at the surface. I'm trying to draw these positive charge being at the surface here, these negative charge being at the surface here. There's one thing I'm going to add to that, the potential. So if the field is zero inside a conductor in equilibrium, then the potential must be constant. inside a conductor in equilibrium. For exactly the region we discussed, the field is the negative slope of the potential. A constant potential creates zero electrical field. So inside conductors is constant potential and zero field. And that's all I really want to add to that story. So whether you're inside the volume of the conductor or onside the surface of the conductor, you'll find a constant electrical potential, and inside the volume you'll find zero electrical field. Okay, here's a quiz question. Let me publish this. It's about this map of the electrical potential as a function of position, the graph of potential versus position, and how it's related to electrical field. Okay, I think I managed to publish that. There were two other regions in the map of potential versus position from 3 to 4 centimeters and 4 to 5 centimeters that we didn't discuss. We discussed 0 to 1, 1 to 2, 2 to 3 centimeters. In those two regions, 3 to 4 and 4 to 5, what is the electrical field? What is the size and the direction of the electrical field based on the graph of the electrical potential? And so you've got to pick one of these four. Okay, I'll get started again. So remember that the electrical field is the negative slope of the electrical potential. The slope here between 3 and 4 centimeters, is downwards, is minus 30 volts per centimeter, which means the field is positive 30 volts per centimeter. The slope here is positive between 4 and 5 centimeters is plus 30 volts per centimeter. So the electrical field is the opposite sign, minus 30 volts per centimeter. So the correct answer is we want a positive 30 volts per centimeter, and it's on this slide here is this fourth answer here. Plus 30 volts per centimeter for 3 to 4 centimeters, minus 30 volts per centimeter for 4 to 5 centimeters. Everybody okay with that? I want to move on, that's the opposite way. I want to move on to talk about electrical potentials of point charges and arrangements of point charges. I want to show you how we picture, the sketch, visualize the electrical fields of point charges. I want to show you the equations for electrical fields of point charges. And then I want to do some examples of electrical fields of point charges. So that's the plan. We'll try, I guess. Okay. This graph here shows you vertical axis is either the electrical field strength or the electrical potential. So something old and something new, versus position, where this position is the distance from a point charge. So this is a visualization, a graph of the electrical field and the electrical potential of a single positive point charge. The field is in red, and that's something we might recall from a couple of classes ago. The field of a positive point charge is Coulomb constant times Q divided by the square of the distance from the charge. The corresponding equation for the potential is very similar but not the same. It's the Coulomb constant times the charge divided by the distance, not the square of the distance from the charge. So you see that both the field and potential depend on the charge. This kind of, you would expect that. Both the field and the potential fall off with distance from the charge. Kind of expect that, but they fall off in different ways. One's inverse square and one's just as the inverse. This, although I'm not going to prove it or establish it, I'm just going to tell you it in words. This electrical field is again this negative slope, the negative slope of this electrical potential. You can sort of see it because where the potential is changing rapidly, you get a strong electrical field. So where the slope is large, you get a strong electrical field. And this is sloping downwards, the electrical potential, which means that the electrical field must be positive, so pointing away from the charge. That's how the two are related. This is another way that we draw the fields and the potentials. So this is the familiar field lines, the orange arrows pointing radially outwards from a positive charge. The dashed blue circles are contours of constant electrical potential. So that's the new thing. Everywhere on a particular circle here, say this one here, the potential is the same. So maybe that one's 2 volts. Maybe this one's 1 volt. Maybe this one's half a volt. So they're contours of constant electrical potential. So when we draw electrical potentials, draw electrical fields, now we're going to supplement the field lines of electric fields with the contours of potential, equipotential for the electrical potentials. This is another way you can visualize it. This is like a 3-dimensional elevation plot. In this, the potential, see, the vertical axis here says volts, so that the height of this curve is the potential. The slope of this curve, where it's steep and shallow, is represented by different colors. So look, it's really steep here, this red region, that's large electrical field. It's less steep here, this orange region, that's a weaker electrical field. Less steep still, this yellow region, an even weaker electrical field, and so on and so forth. So the different colors, red, orange, yellow, green, blue, they describe the slopes, which is the electrical field, which represents the electrical field. This is an arrangement of an electrical dipole. So we've met this before. Water was an electrical dipole. It has a positive charge on the left and a negative charge on the right. And again, I'm picturing both the field lines now. You remember this field line pattern. It's really kind of beautiful, I think. Also on here is the contours of electrical potential. So again, the dashed blue lines, if you walk around one contour, say this one, the potential's everywhere the same on that contour. Maybe this one is 2 volts. And I'm saying plus 2 volts because it's near the positive charge. Because near the positive charge is a hill of electrical potential. Over here on the right, this one might be minus 2 volts. I'm saying that because that's near the negative charge, and around the negative charge is a valley of electrical potential. So positive charges create hills, positive electrical potential. Negative charges, think KQ over R, create valleys, holes over, wells of electrical potential. Here's the 3D elevation map that might give you a better idea. Again, the vertical axis on this map is the electrical potential. So that's vertically in volts, from minus 2 volts through 0 to 2 volts. Here's the positive charge located somewhere in this plane. Here's the negative charge located at a different position in this plane. So they're separated by some distance. This is an electric dipole again. And the positive charge creates a mountain of electrical potential. We've seen this before. The negative charge creates a valley of electrical potential. This is the first time we've seen this. And so you get this so wonderful landscape of this big hill over here, this deep valley here, and these different colors represent different slopes, steep slopes, shallow slopes. They indicate the electrical fields in the different regions. I went through that pretty quickly because that's kind of visualizing, imagining, picturing electrical fields, electrical potentials, and how they're related. I want to get on to, because of the severe panic I'm in right now, I didn't take my medication for coming to class. I want to get on to some quantitative problems. Okay, so I've got a problem here that involves calculating electrical potentials and electrical potential energies of arrangements of point charges. We've just been talking about picturing, visualizing electrical potentials of point charges. Now we're going to calculate some. So in this problem here, I've got 2 charges, Q1 and Q2. One's positive 5 nanocoulombs, one's minus 3 nanocoulombs. Little flecks of dust, right? Pick up charges. That's why things get dusty, especially computer screens. They pick up little charges and they pick up nanocoulombs of charge. So this is like, you know, what a fleck of dust would have. This is a question about the force between the electrical interactions of flecks of dust. Anyway. We've got 5 nanocoulombs on the left, we've got minus 3 nanocoulombs on the right. They're separated by about 1 foot, 0.35 meters. And we're going to figure out a few things here. We're going to figure out the potential at the midpoint, this halfway point here. I'm going to do that first. And then we're going to figure out the energy, electrical energy of this entire arrangement. So we'll do that second. Okay, I'll do the first part on the document camera thing. That's not the document camera, is it? So I started it here. I made the sketch, right, of the left charge, of the right-hand charge, the opposite signs. They're separated by 0.35 meters. I want to figure out what the potential is, V, I'll call it, at this point here. I'm going to use a couple of things. I'm going to use superposition principle. I didn't mention this, but superposition and principle applies to electrical forces, electrical fields, and electrical potentials. So I'm going to use that, and I'm going to use the equation that we met, the new equation, KQ over R for the electrical potential that was related to the old equation, KQ over R squared for the electrical potential. Electrical field. So I'm going to put those two things together. The electrical potential at this point here, based on superposition, is the sum of the potentials due to the point charge on the left and the point charge on the right, Q1 and Q2. I called these two potentials V1 and V2, obviously. Those two potentials are given by that equation, KQ over R, for the electrical potential of a point charge. So it's KQ1 over R, which is actually, let me put in the actual distance, is D divided by 2, because we're thinking about the midpoint. And the second guy is KQ2 over the distance to the midpoint, which is also D over 2. And so that's my expression for the electrical potential. It's based on superposition. It's based on the equation for the potential of a positive charge. Look, we know K, the Coulomb constant. It's a common factor in both of these. We know D. D is 35 centimeters, 0.35 meters, and we want half of that, so it's 0.175 meters. And we know Q1 and Q2, positive 5 and negative 3 coulombs, so nanocoulombs. So I can plug all those numbers in. Again, due to the panic, anxiety, I'm not going to write them all down. I'm just going to write down the answer. For V1, when I did the calculation here for V1 due to Q1, I got 257 volts. It's positive because it was a positive charge. For Q2, that gave me V2, so this piece here, I got what did I get? 154 volts, and it's minus because it was a negative charge. It's smaller than Q2 is smaller than Q1, so the V is smaller. V2 is smaller than V1, but it's also the opposite sign because it's a negative charge rather than positive charge. So the answer is 257 minus 154. That comes out to be 103. Positive 103 volts. And so that's the answer to the first part of the problem. Okay. Everybody okay with that? It's in the notes. What's the potential energy of the arrangement? I'm going to start doing this on the just off the slides. Because I'm going to do this because I've actually got three. Why did I do this? I got three different ways of solving this problem. What is the potential energy? Now, I mean, not the potential, not the electrical potential, but the electrical potential energy of the arrangement of two charges. When you put charges together, you either store or release electrical energy. And so there's some associated electrical potential energy. And that's what we're figuring out. Like when you put masses together, you store gravitational energy. And you might want to figure out how much gravitational energy we store. So now we're talking about energy rather than electrical energy, electrical potential energy rather than just electrical potential. So we're talking about E rather than V, electrical energy rather than potential. Okay. So one way of figuring out the solution to this problem is to imagine assembling the arrangement of charges. This is an arrangement of two charges. There's this one on the left, and there's this one on the right. And we're going to build this arrangement of charges. How would I build it? Supposing you went home and you thought, I want to, that was really interesting about the two charges. I want to build it at home. You get one fleck of dust with 5 nanocoulombs, and you bring that into your kitchen. You put it on the kitchen table. That's the first charge. And then you go off and you find another fleck of dust that has minus 3 nanocoulombs of charge, and you bring that into your kitchen and you put it on the table 35 centimeters away from the previous one. You've built the arrangement of charge. And if when you were doing that, you tracked how much energy did it cost me to bring in the first fleck of dust, that was 5 nanocoulombs, how much energy did it cost me to bring in the second fleck of dust, which was minus 3 nanocoulombs, if you track those amounts of energy, that would be the stored energy. because you can't destroy that energy, you can't create that energy, that's the energy you're going to store. So that's the way we're going to do it. I brought in the first charge Q1 here. And then I brought in the second charge Q2 over here. So that's the way I did it. I brought in the fleck of dust with 5 nanocoulombs, and then the second case, the fleck of dust with -3 nanocoulombs into the kitchen and put them on the kitchen table. I calculated the energy bringing in the first fleck of dust. So this is delta PE1. It's the energy associated with bringing in the first fleck of dust, and then I calculated the energy associated with bringing in the second fleck of dust. So how did I calculate those two amounts of energy? I calculated the change in energy when I put those two charges one by one on the kitchen table. That's exactly what I did. When I bring in the first charge, the other charge isn't there, and so this was our equation that defined the potential, remember. And we're using this equation. When I bring in the first charge, the change in potential for the first charge, when I move it into the kitchen, is actually 0, because there's no other charges around to create potentials. So Q times V, delta V, the change in potential, is actually 0. So there's no energy cost in bringing in the first charge. There is, though, an energy cost. This is the energy cost in bringing in the second charge. It's the amount of charge the second charge has multiplied by the change in potential when I bring it into the kitchen and put it on the kitchen table. Now there is a change in potential because the first charge is already there. So it's got to sit in the potential of the first charge. So to get the energy cost for the second fleck of dust, I've got to multiply its charge times its change in potential, which is the change in potential that's created by being a distance d from the first charge when it's sitting on the kitchen table. So this is Q times delta V, and then I can multiply all this out, and that's the energy cost. And if I add this energy cost, which was 0, the one for bringing in the first fleck of dust, with the energy cost for the second one, bringing in the second fleck of dust, that total energy cost, delta PE1 plus delta PE2, is the total energy stored in the arrangement. And that's how you do it. You might notice, and I wrote it down here, that after going through all these steps of visualizing, assembling the charge distribution, the actual calculation of the energy stored in this pair of charges was actually simply K times Q1 times Q2 divided by D. So the only thing we actually ended up, although it was a long story to tell you about assembling the arrangements of flecks of dust which have charges, the only real calculation was K, Q1, Q2 over D. That's actually the equation for the potential energy of a pair of charges. So I wrote that down here. This is a bottom line, that actually whenever you have a pair of charges, you can calculate their energy by K, Q1, Q2 divided by their separation. You don't have to think every time about assembling the arrangement of charges. It's that straightforward. If you had 3 charges, supposing you had 3 charges, 3 charges have 3 pairs of charges. So supposing you've got Q1, Q2, Q3, you've got a pair Q1, Q2, you've got a pair Q1, Q3, and you've got a pair Q2, Q3. You just add up the energies of the 3 pairs based on this equation. If you had 6 charges, if you had 4 charges, there's actually, if you work it out, there's 6 pairs, and you just add up the energy of all those 6 pairs. So this idea that a pair of charges has this potential energy, you can extend it to any number of charges if you add up all the pairs. I'm going to end there. We talked about energy force concepts, viewpoints. We talked about the electrical potential. We introduced it and how it's related to the electrical field. We talked about visualizing fields of potentials of point charges and computing potentials and energies of point charges. There's one more example in the notes that's about a cell membrane and the electrical potential and electrical energy across the cell membrane. You might want to take a look at that.